Hello. On my last video, I talked about how to solve for the bus voltages using Gauss Seidel. From that last video, I think we were able to converge at 10 raised to negative 6 tolerance after 8 iterations, and then I have given you the value of the voltages by then. So for today, I'll be showing the solution for the load flow of that same system, but instead of using Gauss Seidel, I'll be using Newton Raphson. So I'll still use the same system as before. So I think you may want to recall kung ano yung itsura ng system na yon. It has this admittance matrix. It's a 3-bus system with this admittance matrix. And then from before, I used the following bus designations for bus 1, 2, and 3. Bus 1 being the slack bus 1 being our reference bus for all of the other buses. So it's our reference for the other buses. It's our 100%. Okay, so it's 1 angle 0 degrees. That's slack bus. And then for bus 2, it's a PQ bus. For bus 3, it can be a PQ, it can be a PV, but because of the generator, we'll be treating that as a PV bus. So of course, as for every load flow methods, we'll start with our initialization of the voltages. So for initialization, you want to use, well, we can use any arbitrary value actually. But of course, bakit pa natin pahirapan yung sarili natin if we already have 1 angle 0 or flat voltage? So for buses 1 and 2, we use flat voltage 1 angle 0. For bus 3, we can use 1 angle 0, but because this is a PV bus, you want to maintain the voltage on that bus to be 1.01. So instead of 1 angle 0, we use 1.01 angle 0 on bus 3. Okay, so now before going into the solution of Newton Raphson, I'll be showing you first how do we link the formula from Gauss Seidel, the one that we learned from Gauss Seidel, into Newton Raphson. It's actually quite straightforward because as you can, I hope you still remember, I showed you this diagram for bus 2 on Gauss Seidel, and I told you before that the idea of power flow it's like KCL, but instead of the summation of the currents, we just sum the power, the apparent power. So all of the powers going into the bus or injected into the bus by either your generator or load, well, if it's a load, then it's a negative injection, goes to the network, goes to the lines. Well, in this case, I have a negative injection on bus 2 because I have a load on bus 2, and that negative injection goes to the lines from bus 2 to bus 1 as power 2 to 1, and from bus 2 to bus 3 as power 2 to 3. So I derived this equation before on Gauss Seidel. If you can still remember, this is the summation of the currents on the lines, and then I multiplied it on V2 conjugate. So this and then this is equated to the power going into the system. This is power injected into the system from the load negative injection, which is S conjugate. So take note, I use S conjugate because I use V conjugate I and not VI conjugate. If I use S without the conjugate, then instead of doing this, I don't conjugate V2, but I conjugate this whole term, this whole summation instead. Well, it's a lot more difficult because you'll be conjugating a lot more terms than just using V conjugate I. But well, if you use V conjugate I, then use S conjugate. And now this is where your Newton Raphson, this is basically the principle of Newton Raphson. Your S conjugate here, your S conjugate here, this S conjugate can be represented by its real component and its imaginary component. Take note of the negative sign because this is S conjugate. If we use S, it is just P plus JQ. But because this is S conjugate, then this is P minus JQ. Okay, so I think we may agree that if this is equivalent to this whole term, oops, this one, then I can further dissect this into a real component and an imaginary component. Now, if I dissect this into its real component, then that real component is equivalent to the real component of this one, which is P injected. So P injected can be equated into the real component of this one, and the real I can expand this to show the magnitude and the angle. Take note, this is V2 magnitude angle negative delta 2 because of the conjugate. It's negative. And then for this summation here, this is the expansion of that. We're showing the voltage magnitudes and the voltage angle. So I want to show you the magnitudes and the angles because I'll be using that in the next formulation. So basically, the real component of this whole formula, that is equated to the P injection at bus 2. So if you if you combine all of the magnitudes and the angles, so you just you'll just distribute this V2 angle negative delta 2 into each term here, and then you have a V1 Y21, that's this one, times V2 magnitude, it's because V2 is distributed, angle delta 1 plus theta 2 1, it's basically this angle plus this angle plus this angle, which is negative, so that's minus delta 2, negative delta 2, and then that's that's basically it for all these three terms. Now, what I want to highlight here is that if you show it this way, then the real component of that will just be its cosine. So now you have a V2 V1 Y21 cosine, a V2 V2 Y22 cosine, and a V2 V3 Y23 cosine. Okay, so I think I want to emphasize here that if you have the same subscripts V2 and V2, it becomes V2 squared. Delta 2, it's they basically cancel out. Okay, so now so that's for P injection. So you equate this whole term into the injection at bus 2. Now you do the same for Q, but instead of real component, then it's imaginary. And also, since we are talking about V conjugate I and P minus JQ, Q is not equal to the imaginary but the negative imaginary because of this negative. So you get the imaginary of the whole component and then negate it because of the P minus JQ. Then you equate that to the injected power at bus 2. Okay, so we'll do the same simplification. So you'll have the negative here because of the negative imaginary, and getting the imaginary component of this one, that will leave you with a function in terms of sine. So yeah, so for P you just use cosine because it's the real component. For Q you just use sine because it's the imaginary component. And then you use negative on Q because, well, it's S conjugate and not S. So yeah, that's how you transform your Gauss Seidel into Newton Raphson. And then in the next video, I'll be showing you the how to perform the iteration on Newton Raphson, and then highlight the difference between Newton Raphson and Gauss Seidel.